All right, today we're going to crack open a patent from the 1990s. And inside, we're going to find this brilliant piece of engineering that's pretty much hidden all around us, inside those giant steel towers that power our modern world. It's an invention you've almost certainly never seen, but one you absolutely rely on every single day.
Okay, so let's get right into it. What you're looking at here is called a structured packing brick. And yeah, it's basically a very carefully arranged stack of corrugated metal sheets. I know it might not look like much, but this specific design is a total masterclass in fluid dynamics and, well, efficiency.
So what's the big deal? What on earth does this weird metal brick have to do with something like the fuel in your car, or the vodka in a cocktail, or even the pure oxygen they use in a hospital? Well, the answer comes down to one single, really fundamental process. Yep, it's all about separation. These bricks, they're the high-performance guts inside these massive industrial separators, sometimes called distillation or rectification columns. You can think of them as the unsung heroes that are responsible for purifying and isolating countless chemical compounds we use all the time. So to really get how these things work, let's start with the world they operate in. Just imagine a giant, super efficient sorting machine. The process itself is called rectification. Basically, you start with a mixture, could be crude oil, could be the air we're breathing right now. You heat it up, which lets vapor rise while liquid falls. This packing material, our metal brick, provides a massive surface area for that rising vapor and falling liquid to interact, sorting the mixture out into its pure components with incredible precision. Now, you gotta understand, this structured packing was already a huge leap forward compared to the old way of doing things, which just used a series of simple trays. See, the packing creates a much larger surface area for the liquid and gas to meet, and it has a lower resistance to flow, which engineers call pressure drop. So, long story short, it's way more efficient, but it had a speed limit. And that speed limit created this critical bottleneck that engineers were just desperate to solve. They called it the flooding problem. The patent itself really says it best. The maximum capacity of this whole system is set by something called the flooding point. And that's the exact moment where the whole thing just breaks down, because the two opposing flows, you've got gas going up, liquid coming down, they just can't get past each other anymore. Okay, think of it like this. Imagine a highway where the northbound traffic gets so incredibly heavy that it completely stops the southbound traffic from moving at all. That's flooding. The gas rushing upwards physically holds up the liquid that's trying to flow down, and that causes a backup that just shuts down the entire separation process. It is the ultimate traffic jam, but it's happening inside a chemical plant. Now, this is where it gets really interesting. This slide shows the inventor's key insight. They figured out that the traffic jam doesn't start everywhere at once. Nope. It starts in a very specific place. The base region, right there at the bottom of each packing brick, exactly where the gas first tries to enter. And realizing that, well, that led to an incredibly elegant solution. Instead of trying to redesign the entire brick, they just focused on the one little part that was causing the whole problem. So here's that aha moment. The resistance to the gas flow is at its absolute highest right at the entrance. It's basically a bottleneck by design. The gas has to squeeze its way into all these narrow, corrugated channels, and that's exactly where the backup begins. So the solution was, believe it or not, surprisingly simple. Don't treat the whole brick the same. You just have to intentionally design the bottom few inches, that base region, to be more open. It's like creating a smoother on-ramp for the gas to get into the packing. And by doing that, you delay the start of the traffic jam, and you can push the whole system to run way faster. So how they actually do it? Well, the patent doesn't just give one solution. It actually lays out 4 really clever ways to create this so-called on-ramp. And here they are. First, you can increase the hydraulic radius, which is just a fancy way of saying you make the channels more open. Second, you can make the crimps, the little zigzags, shorter. Third, you can make the angle of those zigzags steeper. Or, and this is the most straightforward, you can just punch more holes in the metal to increase its open area. All 4 of these methods have the exact same goal: make it easier for the gas to get in. This is great because it shows 2 of those ideas perfectly. On the left, in Figure 7, they just stagger the sheets, so some are shorter than others, which effectively doubles how open the channels are right at the base. And on the right, in Figure 12, they just add perforations, or holes, to the metal sheets before they even crimp them. It's a simple way to create a more porous entry point. Of course, an idea is only as good as its results, right? So let's take a look at the data that proves this whole clever fix actually works. This graph, right from the patent, tells the whole story. On the vertical axis, you've got pressure drop. Just think of it as resistance. On the horizontal axis, you've got gas flow, or capacity. Now the black squares, that's case 1, and that represents the old conventional packing. The little X marks, that's case 5. That's the new design with the staggered base. Just watch the lines. As the gas flow increases from left to right, both lines start to creep up. But look at the black squares for case 1. Right around a capacity factor of 0.2, the pressure drop suddenly shoots up. That's flooding starting to happen. Now look at case 5. Its line keeps going much further to the right before it starts to spike, which means it can handle a whole lot more gas flow. So how much more? The patent actually quantifies it. And get this simple, staggered arrangement resulted in a capacity improvement of about 17%. Now, 17% might not sound like a mind-blowing number, but in the world of large-scale industrial processing, getting a 17% gain from such a simple design tweak is, well, it's absolutely massive. So, why should you care about a 17% boost? Well, it means you can get more product, more gasoline, more pure oxygen, more ethanol, out of the exact same piece of equipment. And that translates directly to lower energy use for every single gallon produced, which in turn leads to greater efficiency and ultimately has the potential for lower costs for all of us. And that kind of leaves you with a final thought, doesn't it? This was just one clever fix for one specific problem, hidden away inside one patent. It really makes you wonder, how many other invisible inventions like this are just humming away in the background, quietly and reliably making our complex world work every single day?